Okay, the second part of 6.6 is me dealing with function composition. So let's give a for instance here. What is a composition? Basically, it's like chaining of two things together. So, tickets sold or dollars, how much money per ticket, and then number of tickets sold. And then we can connect the number of tickets sold to the number of theaters showing movies. Another good example, just kind of keeping it simple, is like if you're shopping and you guys are, let's say, something's 80% off, right? Applying that 80% discount to maybe a clothing item, and then maybe you have another 25% discount because your significant other works there as well. So you tack that on afterwards, right? So it's like, just having like multiple things at once. So first and foremost, before we even look at some examples, we got to look at what does this mean, okay? We write composition of functions as follows below. Right, you have a g, and then you have this open dot, and then f, and then x, and all it's saying is we're saying this is g of f of x, okay? And whatever is inside that parentheses there, we are always going to evaluate whatever's inside the parentheses first. So f of x, we always evaluate whatever is in first. It could be f of x, it could be g of x, it could be, anything, whatever's inside. Okay? So the easiest way to go through these problems is to look at a couple examples, right? Because it can be confusing just kind of looking at that. So let's look at a couple examples here to maybe clear things up. All right, we are given that we have two functions, f of x equals x minus 5 and g of x equals an x squared. Okay, we want to know what is g of f of negative 3. Okay, so I approach this problem with an understanding that whatever's inside the parentheses, we're going to evaluate that first. Okay? So we're going to evaluate f of negative 3. Okay? Equation for f of x is x minus 5, so we're going to take negative 3 minus 5, and we get a negative 8. So essentially, g of f of negative 3 is equal to g of negative 8, right? We're just substituting this negative 8 in for f of negative 3. So the output that we get of whatever's inside the parentheses is going to be our input for the function g, okay? So now let's evaluate g of negative 8. Okay, g of x is x squared, so negative 8 squared is going to give me 64. So we find that g of f of negative 3 is equal to 64. Okay, so do whatever's in the parentheses first. Same thing is true for f of g of 2, right? We see that g of 2 is inside the parentheses, so we're going to evaluate g of 2 first. Okay, which means f of g of 2 is actually now f of 4. Right, once again, all we're doing is we're substituting in the 4 for g of 2. Okay, so now we have f of 4. Let's evaluate it. F of 4 is 4 minus 5, which gives me an output of negative 1. So f of g of 2 equals negative 1. Okay? So let's see what happens right? If we look below, I want you guys to try and do the next two on your own here. Okay, you still have f of x is x minus 5, g of x is x squared. Okay, evaluate for part A, where g of f is negative 9, and part B, f of g of 4. Okay, pause the video, try those, and then restart it and check your answer. Okay, so double checking our answers here for part A, we should have gotten 164. Okay, evaluate f of negative 9 first. We get an output of negative 14. And then I'm going to input that in for g. And I find that g of negative 14 gives me 164. Okay. Same thing with part B. Evaluate inside the parentheses first. So for g of 4, we get 16. And then I'm going to substitute that in for g of 4 in my function. So we're actually going to find what f of 16 is. And we get an output that is equal to 11. Okay? So we've used these functions, right? F of x equals x minus 5 and g of x equals x squared. And what we've done is we've evaluated them for specific values of x. But what if I wanted to have the ability to evaluate them for any value of x? Okay? We can find a general rule for both g of f of x and f of g of x. Okay? Remember, if f of x is equal to the following. Okay? And g of x is equal to the following. Then what we're going to do for g of f of x is we're just going to simply take x minus 5 and substitute it in for f of x. So we're going to get g of x minus 5. Okay? Remember, if g of x is x squared, then g of x minus 5 is just x minus 5 quantity squared. Remember, we can rewrite that as x minus 5 times x minus 5. And we get x squared minus 10x plus 25. So for any value of x, g of f of x equals x squared minus 10x plus 25. Okay? And I actually can double check to see if my answer is correct pretty quickly. Okay? Pretty quickly. If I go back up to parts A in the previous two problems, I can actually apply that equation or plug in those values to see if I get the same output. So let's say I did it to part A in the first one. Okay, so I went back to the first one, g of f of negative 3. Okay, if I plug in that equation that we found, I'm still going to get an output of 64. Same thing is going to be true with g of f of negative 9. Right, we got an output of 164 when we solved it earlier, but if I apply it to that formula that we just found, that general rule, we're still going to get an output of 164. So we know that that is the correct general rule for g of f of x. Okay, let's see what we can find for f of g of x. Okay, so f of g of x. And remember, we're just going to be taking this x squared and substituting it in for g of x. So we're technically taking f of x squared. And remember, our formula is x minus 5. We're going to be taking this x squared, substituting it in for x. So we get f of g of x to equal x squared minus 5. Okay, and once again, we can go back and take a look at the previous two examples in part B and see that we will get the same outputs. So I double checked with the first one. Okay, 2 squared, f of g of 2. 2 squared minus 5 gives me 4 minus 5, which is still negative 1. And then if I check with the second equation here, right? F of g of 4 equals 11. F of g of 4 equals 4 squared minus 5. 16 minus 5 gives me 11. Okay, so it works as the general rule, whoops, for f of g of x. Okay, so let's see what happens if we apply these to a real world concept. Okay, we have two coupons, right? We talked about earlier. I got a coupon for $5 off the price of any large pizza, and I also get a 10% discount because I have my student ID. All right, so we're going to see which one's going to be the better deal. Should I apply the discount first and then take $5 off, or should I take $5 off the price and then apply the discount? Well, we're going to see what happens when we do that. We're going to find the general rule for each because we are not given what the price of the pizza is. So we're going to assign a variable to that. We're going to say x represents the cost of the pizza. Okay? And we're going to say that the coupon is going to be represented by the formula C of x is equal to the price of the pizza x minus $5. Right, so x minus 5, price of pizza or cost of pizza minus $5. $5 off. The discount is going to be represented by d of x. And remember, we're taking the original price of the pizza and we're going to be subtracting or removing 10%. 10% off. So 10% as a decimal is 0.1. Right, 10% of whatever the cost of the pizza is. And we actually can rewrite that as 0.9x. Okay, which makes sense. If I take 10% off the price, that means I'm just paying 90% of the original cost. Okay. So we said we want to figure out which one's going to be better to do. What would be better to do first? Apply the discount or apply the coupon? Okay. So let's say I did the coupon first. Okay. Okay, and then I'm going to do the discount first after. And we're going to compare the two. Okay, the coupon first. If I want to do the coupon first, that means when we're talking about composition of functions, I need that to be inside the parentheses. Right? If I want to do the discount first, I need the discount to be inside the parentheses in our composition. So C of x, remember, is x minus 5. So you're going to substitute x minus 5 in for C of x in the first one. So we're taking d of x minus 5. And if we apply the discount first, we're going to be substituting in 0.9x for d of x. So it's going to be C of 0.9x. Okay? Let's see what happens with the coupon first here. Okay, d of x minus 5. Well, the discount is 0.9 times x. So that's going to equal 0.9 times the quantity x minus 5. So we're going to distribute that 0.9, and we're going to find that d of C of x is going to be 0.9x minus 4.5. So here's our equation that's going to represent how much money we're going to save if we apply the coupon first. Okay, if I substitute 0.9x in for our coupon discount, remember that's x minus 5, it's going to be 0.9x minus 5. Right, because we're just plugging this in, substituting this in for the value of x. Right, kind of like we did before here, we had to substitute the x minus 5 in for the x in that equation. So here's my 2, right? This is C of d of x and d of C of x. If I compare the two, both of them, okay, this is representing that 10% off, right? So they both have the 10% off applied, but the only thing that's different is in the second one, we're going to get to subtract only $4.50 off the full price. Okay, if I apply that coupon first. But if I apply the discount first, we get to subtract $5 off. So that's the only thing that's different. I get to subtract 50 cents more. So I'm going to save 50 cents more by applying the discount first. So it doesn't matter what the price of the pizza is, okay? I'm always going to save 50 cents more by applying the discount first, okay?